welcome. My name is Randy Ellis. In this session, we'll review some of the prerequisite materials for nonlinear data analysis, and in this one, we'll review matrix norms. So the main concept is that we view a matrix as a column of vectors. We'll briefly state without proving the Rank-Nullity theorem. We'll recall a vector norm, which is also called a vector magnitude, and then we'll recall a matrix norm. And the main kind of matrix norm we'll use is called the Frobenius matrix norm. We'll mention in passing the spectral norm, also called the L2 matrix norm. So to us, a matrix is an ordered list of vectors. Suppose we have vectors that have m entries, which are size m entries, and a matrix we'll think of having m rows and n columns. So we'll think of this as having n vectors in it. And our block partition will be each column of the matrix is a vector. So here we can say that the matrix A is the vector A1, the vector A2, and so on until we've described all n of the vectors that comprise this matrix. We'll observe in passing, by the way, that means a matrix is a member of a vector space, because we could multiply this matrix by a scalar, and we could also add two matrices that are of exactly the same size. So in a way, a matrix is also a vector. In addition, we have matrix multiplication. Suppose for the moment that we refer to A as having p columns and a matrix B has p rows, we can then use the ordinary rules of linear algebra to define the product of the matrices. The Rank-Nullity theorem is something that we'll just mention in passing. This is as good a place to recall it as any. So let's recall the rank of a matrix as being the dimension of the column space. So it's the number of linearly independent columns in the matrix. If we write this as P, there are a couple of facts. So to me, a fact is something that's true that I'm not going to prove to you right now. And a fact is that the rank of A is also the dimension of the row space. One way we could write that is saying that the rank of A is the same as the rank of A transpose. The Rank-Nullity theorem is that the rank of the matrix, no matter how we mention it, how we measure it, plus the dimension of the null space equals the number of columns in the matrix. This can be shown later on using the SVD if we want. Now let's briefly recall a vector norm. So this is a measure. We write it using double bars around the object, and it has to satisfy 4 axioms that we have gone over in previous prerequisite material. A matrix norm is also a measure, and we write it the same way, and it has to satisfy all of the axioms of a vector norm, and in addition it has to satisfy a 5th one, which is that the norm of the product of two compatible matrices is less than or equal to the product of the norms individually. And we have to read sources carefully. Some sources will refer to a norm for the vectorization of a matrix rather than just for the matrix itself. And recall that a matrix is a member of a vector space, so this sort of thing makes a certain amount of sense, but we have to read quite carefully. So two prominent norms. The first one, which is the most common for us, is the Frobenius norm, and this is defined as the square root of the sum of the squares of all of the entries. You could also think of it as the vector L2 norm of we take all the entries of A and string them together into one gigantic vector. For an orthogonal Q, and if A is not square, we have to remember that these are different Qs, that the Frobenius norm of the matrix is the same as the product of an orthogonal matrix and that matrix, which is also the same as the product of the matrix and any orthogonal matrix. The spectral or L2 norm is much less common, and I'll just mention in passing that if we use lambda submax to denote the largest eigenvalue of a matrix, then the spectral norm of a matrix is defined as the largest eigenvalue of A transpose times A. Here are some properties of the Frobenius norm that's related to eigenvalues. Let's say that we have a matrix B and we write all of its eigenvalues as a vector. Well, and we can also write the singular values this way. So singular values are from the singular value decomposition that we'll look at in a little more detail in a subsequent session. But let's just recall briefly these singular values. So the Frobenius norm is the square root of the trace of A transpose A. So the trace is the sum of the diagonals. So the Frobenius norm can be found quickly by just transposing the matrix, multiplying it in this way, and then adding up the diagonal entries and taking their square root. It's also equal to the square root of the sum of the eigenvalues of A transpose A, and it's also equal to the square root of the sum of the singular values of the matrix itself. So the Frobenius norm is intimately related to the eigenvalues and the singular values of a matrix. Let's look at a very simple example. Suppose that we have this symmetric matrix, so 7, 1, 1, 7. When we compute A transpose times A, we get 50, 14, 14, 50, and that makes sense. Symmetric matrices produce a symmetric matrix. The eigenvalues of this can easily be computed as being 64 and 36. So the Frobenius norm is the square root of the trace, which is 50 plus 50, so that's the square root of 100, which equals 10. And the L2 or spectral norm of this is the largest eigenvalue of A transpose A. The largest eigenvalue is 64, so the square root of 64 is 8. So these norms for this simple matrix are returning different numbers, and in general that's going to happen. So a summary of matrix norms is that the Frobenius norm can be defined as the square root of the trace of the product of the transpose of a matrix with the matrix. It's also the L2 norm when we string everything together, so you can also think of it as the square root of the sum of the squares of all of the entries in the matrix. The spectral norm that we'll use much less often is the square root of the largest eigenvalue of A transpose times A.